Yeah, hello everyone. So this is Dr. Abdul Pasha. Our course is Power System Operation and Control. Here I am going to discuss about modeling of a turbine case. So earlier we discussed about some key points regarding speed governing mechanism and designing considerations under steady state conditions. We utilized steady state models and derived the conditions for swing equation. Consider this. And coming to the case, today's case, modeling of a turbine. So turbines can be modeled in power systems in a number of ways. So which includes component based models, which are also known as white box modeling, and this method involves building a model based on the core component. So here white box modeling, this method involves building model based on the core components that affects the dynamic response. So the model parameters are then calculated or identified based on the measured data. Next are data driven models. These are also known as system identification or black box modeling. So this method uses a general representation of the form of dynamic systems. So like that there may be state space equation or a transfer function. So the model representation parameters are identified based on measured data like PSCAD. That means turbines are represented as dynamic transfer functions in PSCAD. So there are several predefined turbines available in the PSCAD master library. Another case is two-mass systems. So for wind turbine driven trains, two-mass system is coupled through a gear train. They can be used as a model. So the quantities on the wind turbine rotor side of the gearbox can be reflected to the generator side. Some other things to consider when modeling turbines include time constants. So here a simple non-reheat turbine is modeled with a single time constant, while reheat turbines have more than one time constant. Prime mover effects. So in some cases, prime mover effects can be significant even if the phenomena of interest are only a few seconds long. So simulation accuracy is considered here. That is, modeling the turbine dynamics may be necessary to ensure the accuracy of longer simulation studies. So when looking at a single area power system, there are three main components that our literature has a tendency to focus on, mainly governor system that is used for controlling the angular velocity and frequency of the system. Next one is a turbine mechanism. So this is the steam turbine which provides the mechanical torque to drive the generator. And coming to another parameter, generator load, here it will describe the electrical power that is produced and the electrical torque from connected loads. Coming to the turbine model case, now let's consider a fossil fueled single reheat tandem compound turbine. So for that purposes of developing a model, a basic configuration with the components can be represented in the figure. So it contains steam enters the high pressure section through the control valve and the inlet pipe. So here housing of the control valves are called a steam chest, and this HP exhaust steam is passed through the reheater case. So the reheater steam flows into the IP turbine section through the reheat, inlet, intercept valve and then inlet pipe. So the crossover piping provides a path for the steam from IP section to exhaust to the low pressure inlet. So this is the basic representation, whatever we discussed as a fossil fueled single reheat tandem compound turbine. It contains the primary section that will be connected from the boiler, and this is called as a steam chest represented by CV, and it is connected to the HP case and it is tied to the reheater section, and this HP and IP sections are tied to the shaft case, and this is connected through the IP, and this block is connected by crossover section. And this LP sections are divided into two cases, and these sections are again connected as LP sections like this, and these blocks are connected to the condenser sections. So the entire model is representing the fossil fueled single reheated tandem compound turbine case. So here the control valve position denoted with Y suffix E modulates the steam flow that should be going through the turbine for load or frequency control during normal operation. So the response of the steam flow to a change in control valve opening exhibits a time constant that is represented with the TC, and this TCH is due to the charging time of the steam, and the chest and the inlet piping to the HP section. So the intercept valve is normally used for rapid control of the turbine in the event of an overspeed, and it won't be considered in this analysis. Coming to the second section, the reheater holds a substantial amount of steam and has a time constant TRH. So the steam flow into the LP sections experiences an additional time constant. That is a TCO, which is associated with the crossover piping. And the diagram here shows the block diagram presentation of the tandem component reheat turbine. So here this primary section is called valve position, which is containing control valve, and it will be connected to the pi, that is main steam pressure, and it is represented with one of the transfer function 1 by 1 plus STCH. So this is representing inlet steam valve, and the block which is represented here, the chest section, which is connected to the summing point with HP flow. So here RH pressure is considered as 1 by S into TRH, that is the reheater section, and valve positions are fixed here as intercept valve that should be connected to the flow area, and IP flow is connected here, which is connected to 1 by S plus TC naught. This is called crossover section, which is given to FLP module, and the entire block is connected to FHP section, and this is adding to the summation point as a Pmax by MVA base, that is called TMC block, and the entire module is representing the tandem component of reheat turbine case. So to simplify the model, as shown in the figure 2, it is assumed that TCO is negligible in comparison to TRH. So moreover, the remaining two time constants like TCH and TRH has been combined to single time constant TT. Hence, the power output of the turbine as delta PG of S can be linked to the valve position as delta YE of S with the frequency domain. So it will be represented with a simple expression delta F of S, that is KT by 1 plus TT of S into PG of S, which may be treated as equation 1. So here the first expression is representing the simplified model of the turbine in the frequency domain. So whatever the parameters, KT is referred to as the gain of the turbine, and the parameter TT is referred to as the time constant of the turbine. So here block diagram showing the representation with the figure 3 case. This figure is the simplified block diagram of the tandem compound reheat turbine. That is delta YE of S connected to the delta PG of S. This is the entire turbine model KT by 1 plus TTS. So coming to the general case of modeling of the turbine, it is connected by one of the steam valve position, and it is linked with the two stages called HP stage and LP stages. So these are interconnected to the one of the reference point, that is steam valve position, and they will be connected commonly to one of the portion called a reheater. This is connected to one of the portion called reheater. This is a two-stage steam turbine. So coming to here, we need to consider the dynamic response, which is influenced by two factors. That is entertained steam between the inlet steam valve and the first stage of the turbine. Here we suppose to expect high pressure, and in the second case the storage action in the reheater which causes the LP stage lags behind that of HP stage. Therefore, turbine transfer function is characterized by two time constants. That is, for simplicity of analysis, it will be assumed that a turbine can be modeled to have single time constant. So the time constant range is existing in between 0.2 to 2.5 seconds. So modeling of the generator, and the two aspects are there in modeling of the generator case. So one, it should be correlate with the electrical power output consumed by the load, and it will be represented with the classical model or simplified network model. And second one is it should correlate mechanical aspect with electrical output. So likewise, we can extend these two analysis with utilizing swing equation case. Another case is classical model of the generator. So the machine is modeled by an equivalent voltage source behind an impedance, and several assumptions are made in this model. So what are the assumptions we considered here are voltage regulators which are not present and manual excitation is used. This is one assumption, and this implies that in steady state the magnitude of the voltage is determined by field current, so which is a constant parameter, and damper circuits are neglected here, and transient stability is supposed to be adjusted, and it will be simplified by first swing, which is normally reached in one or two sections. So, and fourth consideration is about flux delay in the field circuit, which is going to be neglected, which is happened for a short period of time. And another case is the mechanical power input to the generator is constant, and the mechanical power input to the generator constant means saliency has a little impact. That means it can be neglected in transient stability limits. So another condition is losses are going to be neglected. So these are the conditions it must obey for mechanical power input to the generator when it is going to be maintained constant. And coming to the classical generator model, so generator is connected to an infinite bus system through the two lossless transmission lines. So that is E and XDR follows as constants, and delta is governed by swing equation. We already discussed the swing analysis earlier video. So here which will combine XD and XL1 and XL2 as in the manner of complex parameter JXD. So which is JXD plus JXL1 in parallel with JXL2. So this is to be considered as a simplified model of the turbine model system. So under steady state modeling case, this model of the generator reactance is equal to synchronous reactance, that is XD or XS. So transient state modeling the model of the generator, the reactance is equal to the direct axis transient reactance. So this is also called as constant flux model. Coming to turbine speed governing system, it is associated with one of the block called flyball speed governor. So here linkage mechanism, the flyball speed governor is considered, and in this flyball speed governor, this is the heat of the system, and that may consider one of the main block, and which senses the changes in speed, and as speed is going to be increases gradually, then this flyball will ready to move out. The flyball is ready to coming to out. So the point B moves downwards in the position, and the reverse happens when the speed is going to be decreases. So likewise another block containing linkage mechanism, that is named with ABC. This is a rigid link pivoted at B. So CD is a rigid link pivoted at D. So it provides a movement to the control valve in proportion to change in its speed. So it is also provides a feedback from the steam valve movement. Coming to another block named as speed changer. So how it is associated means we already discussed in the case of speed governing mechanism. So it provides a steady power output setting for the turbine, and its downward movement opens the upper pilot valve. So what happens with this means more steam is admitted to the turbine under steady state conditions. So reverse happens for upward movement of the speed changer case. And coming to another blocks, they are associated with hydraulic amplifiers. So here coming to the main functionalities of hydraulic amplifier, it comprises pilot valves, main piston lower, power level to the pilot valve movement, which is going to be converted into high power level to the piston valve movement. So this is required to open or close the steam valve against the high pressure steam. So coming to speed governing system model, let the operating conditions be characterized by some of the modules. One is flyball speed governor, and this is with the linkage mechanism by flyball speed governor, and this mechanism is going to be considered with a linear incremental model. So if the point A is moved downwards by a small amount, then it is a command which is representing or showing that which causes the turbine output to change. So here flyball speed governor is connected by linkage mechanism by flyball speed governor system. So let us consider that the modal events are represented mathematically. So the movement at A moves C, which in turn moves EF first. Then we see the events contributing to the CT. Then we see that events are contributing to the EEE, which will correlate both and obtain a transfer function. Likewise, we will consider linear incremental model case. Now here two factors are contributing to the movement of the C. That is a flyball speed governor, which is a linkage mechanism to the speed governing system. So it is the amount by which pilot valve is going to be opened. So the movement of this one is the amount by which pilot valve is going to open. So it contributes by C and E portions. So the movement of E can be correlated with the oil flow entering from pilot piston, whose movement is considered with respect to the D. Here one of the assumptions considered for this are inertial reactance forces are negligible, and the rate of oil admitted to the cylinder is proportional to the port opening of the valve case. What are the functions of the excitation system? Here it plays a key role. Based on the excitation system, we are going to decide the response obtained from the turbine model is going to be hikes or decreases. So this model will impact more, and the functions of the excitation systems are considered here. That is to provide direct current to the synchronous generator, field winding, and to perform control and protective functions which are more essential to the satisfactory operation of the power system network. Here we will take some characteristics of the excitation system. That is the basic requirement of a closed loop excitation system. So this is to hold the terminal voltage of a generator for a given set value that is independent of the change, which has to contribute to the following functions in terms of the A parameter, and which will maintain the stable operations of the machine under steady state conditions, transient and dynamic cases. So the A parameter is with the maintenance of stable operations, and B is under steady state, transient and dynamic conditions. So the satisfactory operation with other machines are also considered in parallel with the block C. So effective utilization of the machine also is one of the key factor, which will be capabilities considerations without exceeding the machine operating limits. So these are the parameters we need to select while designing the characteristics of an excitation system. So here some basic parameters that is relevant to the power system considerations. So that is performance requirements of the excitation system, which are determined by generator considerations, which will supply and adjust the field current. So as the generator output is varies within its continuous capability, that will respond to the transient disturbances with the field forcing, and which will be consistently varying with the generator short-term capabilities, rotor insulation failures, due to which high field voltage rotor is going to be happen, due to which heating due to high field current state are heating, and this may due to the high VAR loading effects. So this may affects as one of the power system considerations which influence the system parameters more. And this is due to the heating with the excess flux, which will be considered in volts per hedges. Because of this, the power system considerations, it will contribute to the effective control of the system voltage and the improvement of the system stability case. And here are some of the elements that an excitation system contains. So basically excitation systems are there which are ready to make the connection to the turbine case. It is connected by one of the major component called exciter. So what is an exciter means? It is going to provide DC power to the generator field winding. So here the regulator will processes and amplifies the input control signal to a level, and it will forms an appropriate for control of the exciter and terminal voltage transducer and load compensator case. So here it will senses the generator terminal voltage, rectifies and filters it to DC quantity, and it will compares with a reference signal. Then load compensator may be provided to decide to hold the voltage at a remote point. So likewise the power system stabilizers will comes, so which will provides the additional input signal to the regulator to damp over the power system oscillations. So due to which the limiters and protective circuits are selected. So based on the endurance and capabilities, the exciter and generators are not exceeded. So during the limits, the excitation systems are going to be considered, and they must be treated under these considerations means the power system stabilizers are occupying their locations with the remote point case, and the compensator elements are going to be treated under terminal voltage conditions, and the transducers and load compensators are tied together to make the sensing of the generator terminal voltages, and it will rectifies and filters the unnecessary contents, and which will ready to occupy the positions to make the efficiency of the system to be high. So all these parameters, including the elements, means the exciter will provide more and more DC power to the generator field line. So due to which the excitation system is ready to occupy for the location where it ready to operates under appropriate control conditions. That means whatever the signals generated from the amplifier inputs, they are supposed to be extended to the limit case. That means the compensator is ready to go for the working of the turbine model case. So these are some of the references which I have considered. So based on that, we will take the turbine model with necessary case, and we will extend our analysis with wind and hydel thermal turbine model cases, and how the analysis is going to be generated. So based on that system, we will make the parameters stability constraints. So the factors which are considered are relevant to the system. That means if it is wind system, their parameters are in separate, and if it is normal hydel or wind turbine, hydel or thermal case, their parameters are different. So if it is wind case, then we will use induction generator. So that is the secondary case. But if it is associated with large bulking manner means, we need to consider with the equivalent parameter models. So based on that, the compensator is going to be considered, and the exciter is ready to operate for suitable operating conditions. So here it will provide additional input signals to the regulator, and they are ready to damp over to the power system oscillation networks. So limiters and protective circuits are one of the main components here to discuss with the operating of the excitation system. So likewise, this system can be operated suitably according to the considerations of the parameters. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.